Hello everyone, my name is Osama, and today I'm going to introduce the paper Design Analytics and Data-Driven Collaboration in Evaluating Alternatives. This work is by researchers at the Computational Design Lab at Simon Fraser University. So let's start with a typical scenario in architectural design. There is a group of stakeholders who want to design a building, so they have a set of design targets and objectives, and they go and share these with a design firm. Then, the designers at the design firm start developing a set of design alternatives as well as compute their relative performance. Then the designers want to share these design alternatives with the stakeholders to allow collaboration and to help them to reach consensus about which alternative to go with. But the question is, how? The current collaboration options is to develop a PDF report or a PowerPoint presentation and then invite the stakeholders for a design review meetings, where these design alternatives are discussed and opinions are shared. Or to share this PDF report through email and receive the feedback there. However, this approach is limited due to the overhead and costs of meetings and the limited design presentation and exploration techniques that this meetings offers. Our approach is to develop a system that supports collaboration and decision making throughout the design cycle, from modeling to design presentation to stakeholders feedback to feedback presentation and back to modeling. The design of the system starts from an integration with any modeling environments such as Rhino, 3D Max, Maya, Revit, etc. and the integration of a custom plugin that is responsible for the curation and update of design alternatives to a cloud. Then, the interface called dArt pulls these design alternatives and presents them for stakeholders for design presentation and feedback, as well as designers who can respond to the feedback and see a presentation of all the available feedback. The objectives of the dArt approach is to be able to integrate with any workflow and motivate more feedback cycles, leading to higher customer satisfaction, to also increase the stakeholders' engagement in data-informed decision making, to enable stakeholders to design proposals from any place, anytime, using any platform, and to decrease the cost of in-person meetings. Moreover, to evaluate the alternatives proposed collaboratively by responding to the given feedback, and finally to compile and structure questions, comments, and suggestions for presenting them to the designers at the end of the cycle. There are various examples of systems or interfaces for supporting design stakeholders' involvement in design. In scenarios such as design review meetings, online design modeling, and urban planning. Most of the existing systems are either highly specialized for designers or configured for a particular purpose or design workflow, overlooking other stakeholders' needs. The main gap stays here unaddressed: how to facilitate sharing design information and receiving feedback into the design decision making, considering the stakeholders' diversity and reducing the complexity of the design data. Throughout our research, we use the design study methodology in light of a comprehensive literature review, analysis of multiple collaboration systems, and collaborating with industry partners, as well as using iterative and incremental prototyping for real-world scenarios and cases. We developed and identified 5 high-level requirements. These requirements are used as guiding principles in developing interface features and used in a formative evaluation of dArt. The first requirement is to present each design alternative with customizable visualization of form, performance data, along with the structured stakeholders' feedback. The requirement number 2 is to enable feedback as comments, questions on design form and performance data, and responding to each other's feedback. Third is to allow visual comparison of form, performance, and feedback on design alternatives. And fourth, to be accessible online independent from the design environment, workflows, and system. And finally, to provide adaptable interfaces to accommodate a variety of stakeholders with different interests and backgrounds. DART system has been developed as a classical client-server web application. DART interfaces consist of 4 main views corresponding to the tags associated with these: grid view, alternative view, building blocks view, and conversion view. In the grid view, it presents an overview of all created alternatives in juxtaposed images augmented with controls to access other views. Below each thumbnail image of the alternative, there is an expandable panel tabulating a summary of performance values. Alternative view supports inspection of a specific design alternative through 4 main interfaces focusing on design data, forms, charts, and stakeholders' feedback. Building components view supports inspecting the distinct components of an alternative in detail. A component here can be any cluster of manifold geometry designated with a particular architectural function, such as residential, commercial, etc. This view is composed of a 3D model view, tabular data view, and a feedback interface. Compare view enables the stakeholders to compare multiple alternatives with each other. Presented in the grid view, 2 or more alternatives can be selected, enabling to compare option in the menu. The stakeholders can visually compare form, performance data, and review feedback given to each alternative by other stakeholders. We developed an expert review analysis as a formative method to evaluate DART's current implementation to learn how it supports the proposed tasks. This method is generally used to discover the potentials and issues on the system in the early system development phases. In expert review analysis, we invited 5 experts from the domain of architectural and computational design. The plan was to present the system features for them, then give them a role-play scenario where they act as one of the stakeholders and evaluate the system while being observed and recorded. Then we conclude by a qualitative interview with questions. We conducted a pilot study with 1 expert to assess our method design. In addition to the method's finding, the expert comments hinted at what possible potentials or drawbacks DART might have when other experts complete the evaluation. Due to the time and COVID-19 restrictions, we could not complete the evaluation at that time. However, we believe there is some initial findings that we can share from the pilot study. First, the diversity of form data visualization were found helpful for capturing multiple stakeholders' interest. Also, the consistent use of feedback features encouraged conversations on designs. However, the experts suggested that the feedback functions should better include annotations on form and data visualizations themselves. Also, the converging features can be enriched by adding a component-level comparison within an alternative and across alternatives. Also, adding more features may overwhelm the stakeholders and increase the complexity of the interactions and the traceability of the discussion. Moreover, there were some system features suggested for presenting the feedback to the designers, such as visualizing interaction logs, sending notifications to indicate any activity. Finally, DART was found to be useful in other design fields where projects involve both form and performance data and different stakeholders, such as product design. So in conclusion, as a theoretical contribution, we raise questions about using design analytics for data-informed collaboration between designers and design stakeholders, and we developed a prototype system that aims to support collaboration and decision-making. We found that the primary obstacle in supporting collaborative decision-making on a given set of design alternatives is determining the level of details in design data to be shared with the stakeholders, and that the design of systems that support informing sharing from modeling, design data presentation, feedback, and feedback compilation and presentation requires devising a highly complex computational platform while reducing the cognitive overload caused by the new tasks. In the next steps, we will complete the evaluation with 4 additional domain experts. We will also conduct a formal user study of DART with potential users using real-life scenarios after its refinement, using the feedback from the expert study. We would like to acknowledge Stantec, Mitax, and Boeing for funding this project, and these are our references. Thank you so much for listening, and we'd be happy to answer your questions.